It's our pleasure to invite Professor Onur to give an excellent talk here. And Onur is a professor in ETH Zurich, and he's also a faculty member in CMU. And I imagine pressure that he have participated so many top tier conferences. And I remember that people not only achieve the academic achievement, but also have influenced the industry. And as we know that I remember that several academic achievements have been really deployed in industry products. I think this will be very high impact in both academia and industry. He also received a PhD from the UC Austin, and he received so many academic awards in top 10 conference. And I think that you can read that award is well and appreciated. And he also fellow of ACM and HUE, and I also elect member in academia of Europe. And welcome.
Thank you. Thank you. Okay, let's see. Thank you. Thank you. Can people hear me in the back? Is this good? Okay. Okay, as long as you can hear me, that's good. I don't have a clicker, so I'll stay close to my computer. But it's good to be here. This is my second time in Wuhan. I was here about 10 years ago in 2014 when I visited the university. And I gave a talk, I think, about memory systems at that time. 10 years later, a lot has changed, I think. When I visited 10 years ago, I was talking about in-memory computing, etc. And none of that was happening at that time. Today, I think there's a lot of movement for in-memory, in-storage computation. I'm going to give you some examples of it. But before that, I'll motivate you a little bit. Does that sound good? Okay. How much time do we have? 1 hour, 30 minutes? Okay, as long as I can take, that's going to be very long. But yeah, I think I'll feel free to ask questions in the middle. So if you have a question, please raise your hand. Don't let it wait until the end. I think we have enough time until 12 to handle questions on the talk. And I don't need to cover the entire material. I usually have a lot of material, but let's see. Okay, so today computing is bottlenecked by data. All important workloads are really data intensive, and data is increasing. We can generate more data than we can process in many domains. And we need to perform more sophisticated analyses on data. And both the analysis complexity and data complexity is increasing as we go forward. This is an example from neural networks. Clearly, the computation requirements as well as memory requirements have been growing exponentially, especially in recent years. And the numbers are really large. If you do the calculation, the memory requirements have increased by more than 4 orders of magnitude in only just several years. And this is a slide that I like using. It's a bit old right now because it doesn't go into 2024, for example. But the reason I use this slide is because it's a slide from Cerebras Technologies. These guys are building chips that are this large. And the main reason they're building chips that are that large is so that they can put a lot of computation close to a lot of memory, low latency memory. I will kind of argue that that kind of chip is very interesting to build. But unfortunately, the amount of memory on that chip is still very small. The main reason is the kind of memory that they use. It's an SRAM type of memory, and it's very expensive. And it's very difficult to scale the size of that sort of technology going into the future. So I'm not going to talk about SRAM type of in-memory computing. That's also very interesting, and we do some work in that area. But we're going to look at more scalable, denser technologies. And I think if you really want to push computation to very large amounts of data, we should really look at extremely dense technologies going into the future. So I'm going to talk a lot about DRAM, but there are also emerging memory technologies and flash memory, SSDs, and storage that are also quite interesting. I kind of gave you an overview of the talk using this slide, but hopefully that's interesting. So don't think that machine learning is the only application. In my opinion, actually, there are a lot more interesting applications that we're going to discover going into the future. Genomics is one example. Today, we have actually technologies that look like this. You can put it in your hand. You can buy it relatively cheaply. You can do your analyses, except that is a very good data generator. So we can actually sequence genomes at very high throughput, low cost, As a result, we're sequencing a lot of genomes. Again, this is a relatively old slide also. But the data generation capability that we have with these technologies is amazing, and the cost is reducing. Now, the question is, how do we actually process all of that data? In my opinion, we have a bigger responsibility for the future. As computing and electrical engineers, we're building the infrastructure for the future. And the infrastructure that we're building is going to be used everywhere, literally everywhere. And it has implications clearly on environment and sustainability. And I like summarizing this using a picture like this. Do we want a world that looks like this? Or do we want a world where we cannot breathe in? I used to live in Pittsburgh, and this is from 1920s, 30s, 40s Pittsburgh. It's become much better over time, but I think we need to ask the question. So as human beings, I think we're quite greedy. We want sustainability clearly going into the future, because if we don't have that, maybe we don't have a future. But this should not come at the expense of performance, because we have a lot of problems to solve. And this should not come at the expense of energy efficiency. So we have these three metrics. And I think today we are at a point where we want all of those to be maximized. We don't want a trade-off between power and performance. We don't want a trade-off between sustainability and performance. We don't want any trade-off over here. We want all of these at the same time. Now, if that's what we want, I think what we're doing in the design of our computing systems from the very basics is completely wrong. Meaning, today we have a huge data access bottleneck that affects our performance and energy and sustainability. And the way we design our computers from the very basics is causing a great energy waste, because data is generated somewhere and then moved to a storage and then moved to a main memory and then moved to some SRAM structure and then moved to some register file and eventually gets to a processing place where something can process that data. And once you process the data, you generate some output, and that gets moved back to the output devices, storage devices, etc. So we're basically moving a lot of data. This is consuming a lot of energy. This is consuming a lot of performance. We try to overcome the performance loss that happens because of it, because we realize that there's a huge performance effect of moving this data all around. And we design a lot of techniques to overcome that performance effect. We complicate our software and hardware extremely, in my opinion, to overcome the performance loss. For example, we add heavy levels of multi-threading. We add many, many levels of cache hierarchies that I'm going to show you examples of. We add many levels of prefetchers. We add many levels of metadata management. We complicate our processors a lot. We have heavy levels of out-of-order execution. All of these complicate our systems and make our systems more complex and costly. And usually they don't work. That's the interesting part. We try hard, but the performance cost is still very expensive. And when the performance benefits are not there, energy gets wasted even more. So today we're in this vicious cycle. Because data movement is expensive in terms of energy, we're fundamentally wasting some energy. We're making our systems complex, and that complexity is not buying us performance. As a result, it's wasting energy. So in my opinion, we need to get rid of that vicious cycle somehow. And getting rid of the vicious cycle usually comes from first understanding what is the problem. And I think I've already given you the problem. Essentially, we're processor-centric. All data gets processed in the processor at great system cost. We have to move things to a faraway computing unit from where the data is generated or stored. This is my picture. This is actually a picture that I drew in 2008 when I wrote my first proposal to the National Science Foundation in the United States. This picture is still kind of the same. I was working on quality of service aware scalable memory systems at the time. So we actually were motivating the problem, saying that, oh, we're going to have a lot of cores and memory is going to be a big bottleneck. And we want to actually design mechanisms to make the memory system much more scalable. So the research agenda hasn't changed that much, if you think about it. But the picture has also not changed that much. So this picture is the picture of a processor-centric system. We have essentially cores that process data. These could be accelerators today. They could be heterogeneous. But the point of this picture is that only those cores can process the data. Everything else in this system is really there to store and move data. Caches, interconnects, other caches, other interconnects, other caches, other interconnects, memory controllers, other interconnects, main memory, other interconnects, storage, other interconnects. So if you do the calculation of a single node, and if you include like everything in this picture, more than 95, actually even 99% of the hardware resources are really dedicated to storing and moving data. Now, it's good to think about this a little bit. Like if you give this picture to a 10-year-old child and ask the question, look, child, I'm designing my systems this way. I'm dedicating almost all my resources to storing and moving data. what should be my bottleneck? If this is a reasonably smart child, they'll probably tell you, I don't know what your bottleneck is, but it probably shouldn't be storage and movement of data. Unfortunately, our systems are still bottlenecked by storage and movement of data, memory essentially. I think we need to, going into the future, we should really think about our systems as a 10-year-old child. This is a blank slate. How do I design the system from the ground up? It's probably time to do that exercise, especially if you want all of those metrics to be optimized going into the future. Okay, so you don't like my picture. This is a picture, a recent picture from AMD. This green box over here is just L2 and L3 caches. And most of the rest of the chip is really essentially dedicated to storing and moving data, communication and memory. And we're adding more. We're adding actually 3D stacking technologies, which is very interesting, which is beautiful technology. And those 3D stacking technologies are used to increase the cache hierarchy because we know that we have a big memory bottleneck and we keep adding more complexity to our systems. The question is, should we be using those beautiful technologies to essentially add more of the same as opposed to doing fundamentally different, something fundamentally different? Okay, if you don't like AMD, this is IBM. Again, the same thing happens. The green parts are L3 and L2 caches, but there's a lot of boundaries over here that's really dedicated to memory and communication. Actually, most of the chip is really memory and communication. I'm not even talking about the L1 caches, register files. They're all memory and communication as well. So computation is, in my opinion, a mostly solved problem. Our real bottleneck is somewhere else. Okay, so if you don't like that picture, here's another picture. This could be an SoC. This is a more system level picture. Essentially, we have chiplets today. Chiplets are mostly SRAM. And then you have memory, which is dark. And then you have the darkness, which is storage. I call it the darkness because if you come from like microarchitecture, architecture perspective, this is what people consider the most valuable thing, right? This is what we optimize heavily in most of our systems. This is what really costs a lot in terms of margin, right? But as you go out, things are actually much less expensive, margins are actually much lower, etc. And they're darker in the sense that they cannot do anything. They just respond to this SRAM chip. Okay, so clearly we know that memory is a big bottleneck, storage is a big bottleneck, and people have been working on this. I'll give you some quick examples of this. This is actually a beautiful paper from Dick Seitz. Dick Seitz was the chief architect of Alpha processors in 1990s. How many people know about Alpha? Digital Equipment Corporation, Alpha ISA, not many people. Today the buzz is really RISC-V, of course. Alpha was much better than RISC-V in 1990s. These were real commercial processors that were competing with Intel. And these folks designed some of the fastest architectures of their time. And Dick Seitz led teams that designed some of these processors. And after they designed a flagship processor, he wrote this one-page article. I recommend everyone to read this one-page article. This one-page article says that we designed this beautiful processor. We took a lot of time. It's actually clearly high performance, etc. And it's capable of finishing 4 alpha instructions, every clock cycle. And this clock cycle was fast at the time. Unfortunately, on this important commercial database workload that we believe we designed our processor for, it's finishing one alpha instruction, every 4.7 clock cycles. Basically, this processor is operating at about 5% of its peak efficiency. Why? It's waiting for data to come back from memory. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Again, I think it's, yes, you have a question? That's right, yeah. So the reason he titled this article, It's the Memory Stupid, was because at the time there were elections in the US and one candidate was running by saying, it's the economy, stupid. And he decided to play a joke on that. It's the economy stupid. He changed it. It's the memory stupid. So basically, the joke is that this candidate was saying it's all about the economy. So that's why his focus was on economy. And Dick Seitz decided to say it's all about the memory. We should not focus on anything else, which I agree with mostly. And he makes some extreme statements actually coming from a processor-centric person. That's very interesting. Okay, so that's him. This is me. This is my data from my own PhD thesis. We worked together with Intel at the time in early 2000s to look at what's the bottleneck in microprocessors. And we found out across all of the large number of applications that they used to design their processors at the time, the processor is bottlenecked by memory. Most of the time, the processor is waiting for data to come back from memory. Okay, you don't believe the Excites, you don't believe me, since everybody believes Google or a version of Google somewhere. This is data from Google. It's a beautiful paper. They published in ISCA 2015. They essentially show the same thing. According to their results, according to all of their data center workloads, the processor is most of the time waiting for data to come back from memory. It's doing what it's supposed to do, meaning completing instructions only 10 to 20% of the time. Now, again, take the stand of a blank slate. We don't know anything. We're a 10-year-old kid, although today's 10-year-old kids know a lot, I think. Maybe go down to 6-year-old. Ask the question. I designed this thing. This thing is supposed to finish instructions. It's finishing instructions only 5 to 20% of the time. It's doing what it's supposed to do only 5 to 20% of the time. Is this thing good? Probably they'll answer it's not a good, right? Hopefully. And it's good to be honest with ourselves, I think, going into the future, just like a 5 or 6-year-old kid would be. Basically, we're designing not so good systems. In a sense, these are actually extremely advanced systems, but they're not good. They're not efficient. They're really not doing what they're supposed to be doing, because I think we have a fundamental problem to begin with. Okay, so that was performance. Let's talk about energy. Most of the time, people talk about performance and they forget the energy and complexity. But we're not going to forget it because this is much worse. If performance was bad, energy is much worse. So this is data from Bill Daly. You can argue with all of these numbers over here. I will not go through a lot of detail over here, but basically today, computation is not a problem in terms of energy. We have solved that computation problem with technology scaling and other optimizations a lot. There's more to do, of course, but the real bottleneck lies somewhere else. Whenever you're communicating data, accessing data, in this case, accessing DRAM, a single DRAM access costs more than 100x the energy of a sophisticated arithmetic operation. Now, does it make sense to actually do many DRAM accesses to do 1 or 2 arithmetic operations? If this is the optimization, of course, it's an optimization problem, right? When do I want to bring the data to the chip to do this operation that's not costly in terms of energy? And you can formulate this. This is a beautiful exam question, actually, in a computer architecture exam, in my opinion. You can do the calculation easily to figure out how many times do you need to reuse that data on chip so that you can amortize the cost of energy. And that number tends to be in the order of thousands today. Okay, so this is complicated arithmetic operations. Let's talk about simpler arithmetic operations. So this is a 32-bit integer addition over here. The disparity of energy of a memory access is 6400x, according to some of those numbers. Again, take these with a grain of salt. Energy always changes with optimizations, etc. But the order of magnitude is at least 3 orders of magnitude. A simple arithmetic operation is at least 3 orders of magnitude cheaper in terms of energy than a DRAM access. And today, for good reason, people are trying to reduce the width of the arithmetic operation. We don't want to operate on 32 bits. We don't want to operate on 16 bits. We don't want to operate on 8 bits. We don't want to operate on even 4 bits today. We want to operate on 2 bits, 1 bit, right? Why? Because these are expensive things. And we figured out that they're expensive things, especially because of data movement. Once you reduce the complexity of the arithmetic operation, both data movement reduces and also computation complexity reduces. But unfortunately, data movement still remains because of the granularity at which we access the memory system, which we may get into later on in this talk. I've also mentioned one more thing. That number is ignoring storage. If you actually talk about moving the data from the storage, add another at least 10x over there, and the number goes crazy. Do I want to actually spend 64,000x energy to do one arithmetic operation? It's good to ask that question. Okay, so we did a lot of studies to quantify the cost of data movement in real systems. I'm going to mention 2 studies that we did with Google recently, actually not so recently anymore. This is from ASCOS in 2018. We studied the workloads that people use on their mobile computers, Android phones, or Chromebooks. Some examples are, for example, YouTube, machine learning inference, like TensorFlow at the time, video encoding and decoding, and we found browsing also. We found out that under normal conditions, not so aggressive, not so intensive conditions, most of the total system energy spent on data, more than 60%. In some data intensive cases, this number increases significantly. If you go to accelerators, machine learning accelerators, we repeated the study with Google Edge machine learning models and Edge machine learning accelerators, Google Edge TPU, if you're familiar with it. And we found out that more than 90% of the total system energy is spent on memory in these large machine learning models. And if you're interested, there's a lot more data in the paper. I'm going to mention this paper later on when we get to near memory computing and its examples. But this is one example result that we have in the paper. At the time, these are proprietary models that are used at Google at the time. And we have LSTMs and transducers. These are the largest models at the time. And if you look at these results, most of the energy is spent on DRAM and off-chip interconnect, assuming you optimize everything to fit in your DRAM to begin with, which is what you would like to do in HTPUs, etc. Okay, so basically, I could keep going and giving you a lot of results like this. I'm not going to do that right now. But the problem we have is we're processing data far away from the data. And we need to change that. We basically need a new paradigm of designing computers, which enables computation with as minimal data movement as possible. And we want to compute where it makes sense, where data resides. Today, we have no choice. We have to enable the choice so that we can compute everywhere in the computing system design that we have. Then this leads us to computing architectures that are much more data-centric. So this is then, again, a SoC example. Today, we're actually limiting computation capability to a very small fraction of this SRAM-dominated chiplet. But we have many other places to do computation. And our vision is that you should be able to do computation everywhere and then schedule the appropriate task to the appropriate place to do the computation in. And of course, this requires a lot of changes across the stack. We're going to see some examples, both small examples and large examples that lead to a lot of different changes. And in all of these changes, I'm going to think about memory as an accelerator in the sense that today we're building a lot of accelerators, right? And we have realized that building accelerators is important for efficiency performance. Basically, what we're going to propose is not going to be as radical in that sense. In the sense, we would like to have acceleration capability on the memory side. We want to have accelerators on the memory side, and we want to have more sophisticated accelerators. So think about an ecosystem where you don't have accelerators only over here, but also on the memory side, also on the storage side, also on the sensor side. So everywhere has a lot of acceleration capability. Okay. There's clearly some other way of thinking about memory-centric computing, which is you don't really have a central processing core. The CPU is gone, and everything is a distributed agent, and everything coordinates with each other, and you have a programming model that enables that coordination. I'm not going to go there. That's more distributed, less accelerator-centric. We're going to still stick to the accelerator-centric type of paradigm. Okay, so our goal is to really enable processing inside memory and storage. I'm going to focus more on memory today, but we do a lot of work on storage also. I think, in my opinion, these two things are essentially the same thing with different trade-offs. We would like to be able to ask the question, memory, can you accelerate this function or this application or this instruction for me? And when the memory or storage says yes, they will also return the results. Clearly, there are many questions over here. How do we design the processors? How do we design the memory and storage? How do we design the communication units? How do we design the software and hardware interfaces to enable this? After that, how do we design the system software compilers and languages to make this easy for a lot of people? And then how do we design our algorithms to take advantage of the computation capability over here? So it's essentially across the stack problem, which is fascinating and which is great, I think, for research. And we should be doing a lot of research. I'll give you a lot of examples over here. I will mention one more thing over here just to hammer home how processor-centric we are. How many people here have taken a theory of computing course? Computation theory, algorithmic complexity? Probably some people. No? Okay, I see some hands like I'm not going to ask you questions on to compute the algorithmic complexity of an algorithm. Don't worry. But I assume a lot of people have taken it. If you have an electrical engineering background, maybe you haven't taken it as much. That's okay. Don't worry. Basically, today, if you want to, the foundations of theory of computing is really very processor-centric. When we actually compute the complexity of an algorithm, for example, we count the number of operations. And that number of operations is a very processor-centric paradigm if you think about it. Everything I showed you earlier says maybe we should really be focused on the data. Right? We're really focusing on the operations as opposed to data, if you think about it. So I think we need to actually build a very fundamental theory of computation that's very different from what we have today. And I don't believe people are working on this as much. There's a lot of work that is going on the practice of near memory, in-memory computing, as we will see. But the theory is missing, in my opinion. And maybe that'll come later. Hopefully, there will be some people inspired who would actually work on it so that theory also catches up with practice. Okay, so I should also say that what I'm going to talk about is not a new idea. There have been a lot of smart people in the past that have thought about how to organize computation. This is the oldest paper I could find that is similar to what we're going to talk about. Basically, people have thought about how to put computation closer to memory. This is an example of near memory computation. This is a beautiful paper from 1960s. And another paper, another person whom you may be familiar with, Harold Stone, wrote a paper in 1970s also. Harold Stone has a beautiful textbook on high performance computer architecture. If people are interested in architecture, I would recommend that textbook actually. It's a bit dated right now, but it has a lot of fundamentals in it. Okay, so this is an old idea. People have looked at it over the years. What has changed today? So let me talk about that a little bit because it's also a fascinating story. I think I've already given you what has changed today from the application and system perspective. From the higher levels, we need to do something different because we have huge bottlenecks for data access and we want performance, energy, and sustainability all at the same time. And we can improve all of these metrics by minimizing data volumes. But from the lower levels, we also have a problem, which is we're having huge problems with memory technology today. So I'm going to spend the next 5 minutes or so talking about that because I think that's really important and that's fascinating. We really need to think about what's going on with the memory technology. We should look at new technologies. But I think in the end, as memory technology scales so that we push denser and denser memories, high capacities, technology scaling will always come and haunt us, meaning we'll have a lot of problems. I'll talk about the RowHammer problem in DRAM very quickly, for example. These technology scaling issues can be solved by better computation, better partitioning of tasks between the memory and the controller. Now, if your controller is capable of computation, it's programmable, it's patchable, etc., you can have a much more scalable memory technology at the system level from a system perspective. And there are emerging technologies that are also quite interesting, and these can enable new functions in memory, for example, like 3D stacking technologies or emerging crossbar type of technologies. So I think technology and computation interplay is going to be very interesting. But basically today, in my opinion, we have nowhere else to escape. Applications and systems are pushing us to do something different. Technology scaling issues are pulling us something to different. We're kind of squeezed in the middle. That's why I think in-memory computing is happening right now, and it's going to happen more and more. Any questions before I jump into the technology scaling push? So I'm going to give you a very low-level perspective. Essentially, we have a lot of problems with technology. We've been working on actually DRAM and flash technology. I'm going to focus on DRAM for this talk. Flash is also fascinating. SSDs are also fascinating. But let's talk about DRAM. So essentially, because we are able to push a lot of cells in a given millimeter square today, we're having a lot of problems. One problem is you can predictably induce bit flips in commodity DRAM chips. Essentially, with legal access patterns, you can induce bit flips, data corruption. This should not be happening. All recent DRAM chips are fundamentally vulnerable according to our many results. And what's also interesting is this is a robustness problem. It's really a technology scaling that affects robustness, but it's also the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And I like this article that says, forget software. Now hackers are exploiting physics. This is kind of the security perspective. So if you have a bit flip, you can do a lot with that bit flip. Let me give you the fundamental problem. The fundamental problem is read disturbance. Whenever you access one cell in memory, you perturb things around it, including cells around it. So in DRAM, this is very fundamental. Any memory technology has this problem. The question is, who does this get exposed to? Can you fix it at the memory controller level, or should this get exposed to the user? If this gets exposed to the user, this is very bad because now the user needs to take care of these bit flips, right? Okay, in DRAM, if you want to access a row is a one-dimensional array vector of cells, and then a subarray is really two-dimensional array of cells. You need to activate the word line, apply high voltage to the word line. You open the row. Now you can access a cell after that. Now, if you want to access some other row, you activate some other word line. So you need to close this row. We need to apply low voltage to this word line. Now, keep doing this repeatedly causes perturbation. Now, if you keep doing activate, pre-charge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, this is legal in real programs. It turns out vulnerable cells and physically adjacent rows get corrupt. They lose their charge little by little. And if you do this enough times before the cells get refreshed, you get data corruption. And essentially, these become the victim rows. Now, these victim rows may belong to some other application. They may belong to the operating system. They may belong to a machine learning accelerator with weights that may be important that should not be modified. They may belong to some security critical application that stores some keys, for example. And as a result, this should not be happening. But we showed that this is happening in essentially all real DRAM chips. And this is becoming worse as the cells become smaller and closer to each other. This disturbance effect is becoming worse. So we have shown in recent years that over the course of about 10 years, we've seen a 100x reduction in the number of activations that are needed to induce a bit flip in DRAM. These are the result from real DRAM chips. So today you can induce activations with only 100, you can induce bit flips with only 100 activations or so, if you know what you're doing. Okay, so this is RowHammer. Again, I could talk a lot about RowHammer, and that's the original paper that I mentioned over here. A lot of work has been built to show that this is not a good, essentially a lot of work has happened to show that this is not a good thing. Clearly, it's not a good thing. It should not be happening. In security, for example, people have shown that you can take over a system using these bit flips. You could read data that you do not have access to. You could break out of virtual machine sandboxes. You could corrupt important data and render, for example, a machine learning inference useless. Think about having this in your self-driving car that takes advantage of a lot of inference. You can steal secret data like cryptographic keys or ML model parameters. In fact, hackers have been making jokes that look like this. This is a famous hacker on the internet who said RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you're after. I like this one. So if we're in this room, for example, and if the doors are closed and we cannot get out, keep banging on the walls. And if you do enough banging, maybe one of the doors will magically open. That's kind of the disturbance effect, right? Okay. So well, the door has closed, as you can see. Maybe it has a mind of its own. So as I said, there's a lot of research that's going on this topic. We have written articles, surveys. If you're interested, I'd be happy to talk about it more. We talked about how to solve it. So without going into a lot of detail, why am I telling you this? Essentially, the reason I'm telling you this, these issues are going to happen more and more. And these issues require computation capability inside or near memory. Essentially, we call this intelligent controls. And we've been calling this for a long time now. This is an early paper where we discussed this. Now, what's happening in industry? Finally, similar solutions are being deployed in industry. This is a paper from last year, ISSCC 2023, from SK Hynix, a major DRAM manufacturer. And essentially, they wrote a paper acknowledging that RowHammer is a serious problem. And one solution that they're pursuing is to put computation capability inside the DRAM chips. These are DRAM chips. Well, this is a picture of a DRAM chip. They're essentially adding a controller inside the DRAM chip to detect when a row is being hammered. And if a row is being hammered, they take some mitigating action in this controller. So they actually count activations to rows. Now, this is actually interesting because DRAM manufacturers never want to put any capability in their DRAM chips. They just want access capability. Today, they are putting computation capability. This is what I'm really, what I really wanted to show. And we're in 2024, so I can show this picture to you. If we were actually in 2015, when we were arguing this should be happening in real DRAM, you wouldn't have this picture. But basically, today, we're putting computation capability inside the DRAM chip to solve these problems. In my opinion, we should not stop here. We should say, okay, we're putting a lot of computation capability inside the DRAM chip. What else can we put over there so that we can make our life easier at the higher levels and be fundamentally more data-centric? Okay, so this solution is being adopted by JEDEC, which is the main standard body in DRAM. And you can read a bunch of our papers. The question I will ask is, though, this is not going to end here. I believe there's a lot more that we're going to see. And it's always good to ask when people develop solutions like this. In my opinion, this is a step in the right direction. Are the solutions good? So you have this fence protecting this road, right? Is that a good solution? No, maybe not, right? So we have been looking at other effects of scaling in real chips, and we found another one, row press. I'm not going to go into the details of it, but this paper shows that you don't need a lot of activations to induce a bit flip. You basically open a DRAM row, keep it open for a long time. Now the fact that you keep the DRAM row open for a long time induces disturbance. And you don't need that many activations. You can reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude, showing this. I believe there are a lot more effects like this. And if these effects are not taken into account in your controller, then your solutions will not be good. Okay, there's about a lot of my students work on similar topics on this area, and this is a very recent PhD thesis from one of my PhD graduates. If you're interested in RowHammer, I'd recommend that. But I believe there's more to come. Okay, before we move on, I should say something about emerging technologies. Emerging technologies are very interesting. You can always say DRAM, flash, these are old technologies. Let's not work on them. We're academics, we should be working on the future. And I agree. Well, not completely. I agree partly in the sense that saying that we should be working on emerging technologies, but we should also be working on existing technologies because these existing technologies are very, very interesting. And they can also teach us a lot about emerging technologies. So if you look at emerging technologies, they're actually very interesting. But unfortunately, they have other problems also, like endurance, etc. And they all require intelligent controllers. This is one example paper that we have written a long time ago right now. Basically, they require intelligent controllers for other reasons as well. And they also require intelligent controllers if they scale to the same levels of DRAM and flash that we have today. Today, we've scaled DRAM and flash to levels that we've never scaled any other emerging technology to. When you scale an emerging technology to very small sizes like we have, DRAM and flash, they're going to have very similar issues that will require similar solutions. Okay, so I kind of covered the memory technology part. I've kind of covered the first part. So hopefully you agree that we have nowhere to escape today. Then we're going to talk about some ideas on processing in memory. Any questions before I jump into some ideas over here and maybe define some structure to this? There was only one question from a professor. What about students? Okay, no one yet. Don't be shy. Okay, there you go. Yes. Hmm? Yeah. Yeah, I mean, companies can do different things for different reasons. That should not be a reason to not investigate different technologies. So in my opinion, again, I don't know exactly why Intel cut off their technology. They have a lot of things that go into that decision, clearly. But I believe fundamentally, we should be investing into finding new technologies that could potentially be better, that could complement our technologies. So that should not be a limiter for our research. Okay, good question. Okay, so now I'm going to go into the meat of the talk where I'm going to talk about different types of processing in memory. In my opinion, there's only two fundamental types. One is processing near memory and the other is processing using memory. And these are different. And old papers on this topic are about processing near memory. Because processing near memory is actually more, let's say, conventional. You have logic as we design today. You have memory as we design today. And you put the logic closer and closer and closer and closer to memory. In fact, today we're doing processing near memory, except near is very far. You have logic, you have memory. Today we're far. Put the logic closer, it becomes processing nearer to memory. Put the logic a bit farther, it's worse than today. We don't want to be there. Just to give you a slide over here, you have computation logic that's closer to memory, inside the memory, in the logic layer of 3D stack memory, etc., near the bank, near the subbank. The other type of approach is fundamentally different, which is longer term. It's harder to achieve, but it should also be done, is processing using memory. And processing using memory says you have logic, you have memory. Forget about logic today. We have memory. Memory itself can function as logic. Essentially, you can use the operational principles of memory cells and circuitry to perform computation. This is something that has not been as taught as much in the past. This is happening a lot more since 2010s or so. And I think it's fascinating. I think both of these are important to make happen. The first one is easier. The second one is harder. And in the end, I think we need to combine them. Okay, because the first one is easier, I think industry is taking up the first one much faster than the second one. So when I gave this talk 10 years ago in Wuhan, none of this was there, except for the 3D stacking technology that I used to motivate, saying that, oh, we should be looking at these technologies and doing some computation inside there. Now, in 2024, we have prototypes from UpMem, which essentially sells DRAM chips with computation capability inside them. And we have machine learning accelerator near DRAM bank. You have computation capability in these processing in memory chips, DRAM chips essentially from Samsung, SK Hynix, Alibaba. And then there are also other things that people are doing near memory, which is you have an FPGA next to many memory chips over here from Samsung, for example. I will not talk about these industry prototypes as much, which is interesting, I think. And we have a lot of results on some of these chips like UpMem, and I'd be happy to talk about this. And also in industry, I think there's also another movement, which is nice. You have more flexible interconnects. CXL, Compute Express Link, is one example of a flexible interconnect that enables you to offload computation somewhere else other than the processor. And going forward, in my opinion, we need to have much more flexibility in our systems to do computation somewhere else. Okay, and there's more papers. Let me give you some example results very quickly. I'm going to first talk about processing near memory, but I'm not going to focus hopefully too much on that. I'm going to focus a lot of my time on processing using memory and give you some results from real DRAM chips or recent DRAM chips. But I think processing near memory is also interesting, and we should revisit it again because their technology is changing. Essentially, today, we're much more closer to what we have envisioned more than 10 years ago. Essentially, you have 3D stacking technologies where you have a logic layer under memory layers. And this logic layer can have high bandwidth, low latency, low energy access to reasonably large capacity memory on top of it. And we can hopefully make this logic layer much high quality in the sense that it's going to be very similar to the logic that we use to design our processors, high performance processors with. And I believe that strongly. And there are other true three-dimensional technologies that are under development that can enable much better access, much better connectivity between logic and memory by reducing the width of these connections from the top down. So monolithic 3D technologies, for example. So I'm going to give you some example results that we have collected over the years. This is a work that we've done in starting from 2012 or so. The paper was rejected multiple times, so it got published in 2015, as you can see. But the basic idea is take these 3D stacked memory plus logic chips and put them together as an accelerator that can accelerate an important application. At the time, the application for us was graph processing. But I think there's nothing that makes this, this is also applicable to machine learning, large language models, et cetera. And people are actually doing work in that area right now. The basic idea is in the logic layer, you can put processing capability. In this work, we put a parallel processing capability in order cores. You have many in-order cores connected via some network. And these in-order cores, actually, each in-order core controls a memory on top of it. And when you actually want to do something to the memory location that a core houses, you send a message to that core. You basically ship the function to the data as opposed to shipping the data to the function. And we have a programming model using remote function calls to enable this. And this is actually useful in graph processing because graph processing, there's a lot of random accesses, and updates to graph nodes have a lot of random access bottlenecks. So if you actually ship the updates to the place where the data is, you minimize the data moment. And of course, one of these chips is not enough to house a large graph. So you need to have a distributed system of these chips. And the way we envisioned at the time, this accelerator was, it's kind of like a primitive GPU at the time. You offload your graph computation, you map your graph on top of this, and computation happens using remote function calls to update the graph nodes, which is very interesting. And we have good results, as I will show you. We have some prefetching mechanisms that I'm not going to talk about. This system doesn't look like any existing system at the time or today. Today, we're closer to near memory computing, of course. So all of these prior systems that we compared to have the memory bottleneck or memory dichotomy. There's a difference between processor and memory. But if you look at Tesseract, compute and memory are coupled, and you have a distributed system of these compute and memory, near memory computers, essentially. And as a result, you get very high bandwidth access to a large amount of memory. And this is reflected in performance. You see significant performance improvements on average across 5 graph processing algorithms. Later works improved on our work. The numbers after, let's say, 5, 6, 7 years have been, we're closer to 100x, essentially, if you actually specialize even more. And the energy reduction is also significant. We get more than 8x energy reduction at the time. Later works also improved on our work. Remember that this work was done more than 10 years ago. In fact, I gave briefly the basics of it when I talked in 2014. Now it's published. It was not published at the time. But basically, later works improved this to almost 100x. So my point is, without even thinking, by going to near memory computing, you can improve performance by about 2 orders of magnitude and energy by 2 orders of magnitude, if you actually do a lot of specialization. Okay, this is the paper. There's also a shorter version of it if people are interested in reading it, and not long papers. I guess today you can feed it to a ChatGPT type of engine, and it could give you a summary and it could tell you about it, but it may be wrong. It's good to always think about that. Okay, so we actually do more work in this area, which is actually very interesting. If you go and change the algorithms and specify the algorithms in a set-centric manner and change the instruction set architecture such that sets are a first-class data structure, you can express a lot of graph algorithms using sets. And sets are very nice to accelerate in hardware because they're bitwise operations. You can actually use processing using memory as well as near memory for it. In this work, we really have a fully across the stack design for graph processing. If people are interested, I'd recommend reading it or talking with me. As I will show you later, bitwise processing is actually very efficient in memory. And in my opinion, maybe we should be rethinking our algorithms going into the future such that they're more bitwise based so that we can reduce the complexity. Okay, let me give you one more example, and then we're going to move to processing using memory. Any questions before that? So we have had 2 questions so far. Maybe we're going to increase the number. Not right now. Okay. Okay, so I'm going to talk about neural network inference. This is the second work that I mentioned that we did with Google on understanding the impact of data on devices. This is a very quick summary of it. We essentially analyzed the Google Edge TPU using 24 Google Edge models, and we found out that it's designed for computation and not for memory. So it's very heavily memory bottlenecked. And the reason is different models have different requirements, whereas this Edge TPU is really designed as a compute-centric thing that doesn't cater for those requirements. It's very monolithic. So we provide a new machine learning accelerator framework. It could be applied to other accelerators, in my opinion. Essentially, you have heterogeneous accelerators. Some of them are compute-centric, some of them are memory-centric. You put them together, you partition the workloads and layers and models to these different accelerators. And then the main results show that you can improve the performance by about 3x and efficiency, energy by 3x also. At the same time, you can reduce the hardware cost. Meaning, yes, you design 3 different accelerators, but overall, the cost of those 3 different accelerators in terms of hardware area is smaller than a monolithic machine learning accelerator that we designed today. So that's very interesting. You can improve performance, energy, and area at the same time. Complexity increases, of course. That's a different question. Okay, let me give you a quick overview of this. Essentially, we analyze a lot of workloads that are used in the field, and we try to understand the diversity across the models, and we found out there's significant variation in terms of layer characteristics across these different models. So if you look over here, the parameter footprint of these models is very high, and also arithmetic intensity, how many operations that you do on a given byte is very low. So these are very intensive, memory intensive models, as you can see, whereas there are some other models where the arithmetic operations that you do is a lot and memory parameter footprint is very low. And designing a single accelerator that's good at both these type of models and these type of models is extremely difficult. I would almost say impossible to do. You can, of course, go to reconfigurability, but reconfigurability has its own overheads. Okay, so even within a model, if you look at, for example, layers from a neural network, there's a huge variation in terms of arithmetic intensity over here, flops per byte, and there's a huge variation in terms of number of operations. Again, designing an accelerator that's good at this point and this point at the same time, a single accelerator is very difficult. That's why we go into a more heterogeneous design. Instead of designing a single monolithic accelerator that's good at everything over here, we partition the design to families. There's a compute-centric accelerator over here, and there are 2 data-centric accelerators. Of course, you can have more families. In this case, we restricted ourselves to 3 families that we think that covered what we're looking at. And the runtime system, the scheduler, software, hardware, cooperatively decides which layer should be executed on which type of accelerator. And you can see that this compute-centric accelerator can now be much smaller because it's really catering to compute-centric layers that are extremely intensive in terms of computation. And it's not trying to overcome the data movement bottleneck. Some other layers that have the data movement bottleneck are shipped to these data-centric accelerators. I will not go into the design of everything over here. The paper has a lot of details. You need to identify the layer families. This requires profiling online or offline, but you could do some identification. Once you do the identification, you ship the appropriate layer, appropriate family of layers to the appropriate accelerators. And once you do that, the results look pretty good. I think we can improve that even better. So basically, we see that you can reduce the energy consumption on average by about 3x compared to baseline HTPU. On intensive models, the energy reduction is actually more than 5x or so. So intensive models are actually even worse. I believe we didn't have LLMs at the time, but LLM inference is actually even more intensive. And you see, we see today we have actually some results, and with LLM inference, we get a lot higher energy improvements as well. So performance also improves. We can improve performance by also more than 3x. This is throughput. Latency results are in the paper. You can also reduce latency. Again, I will not go into a lot more detail, but this is an example of a heterogeneous design that combines compute-centric accelerators with memory-centric accelerators. Any questions? Yes, please. Sorry, what's very tough? Yeah, thank you. Sure. Yes. Yes. Yeah. So I think yes, basically. But for example, this paper shows that you can improve performance, you can improve energy, you can also reduce area cost, which is important for sustainability. I think sustainability we don't quite understand yet. People are developing metrics, etc. But energy goes into it, area cost, hardware cost, lifetime, etc. All of them go into it. And I think this type of data-centric design is definitely in that direction. And we're just scratching the surface, in my opinion. If you actually look at how we design the systems fundamentally from a data-centric manner, I believe we can actually improve all of those. In fact, we have not, I think, talked about, this is an example that shows that you can reduce the accelerator complexity. But if you start looking at the general purpose system, another question becomes, what can you remove from the processor today once you have memory-centric processors or accelerators? And that becomes a very interesting question, because in my opinion, today we complicate our processors too much to overcome the data problem. Okay, so there's more work that I'm not going to go into because I want to focus on something else in the rest of the talk, and feel free to ask more questions later. I mentioned this, you can accelerate mobile workloads. And I should say that in this case, what we did was not changing the system completely. We're really doing function or layer offloading to different accelerators. You don't need to have a different programming model over here. You need to have a different runtime, yes. Here again, we don't change the system completely. We do have work on processing in memory for genomic acceleration. I don't have time to talk about it, but I think this is very fascinating. We do have work on the in-storage computing for genomic acceleration. That's also very interesting, but I'd be happy to talk about that separately. This is our recent work on metagenomics acceleration in storage. And in some cases, the amount of memory that you need over here is hundreds of terabytes in terms of genomic data. And actually doing processing across all of those hundreds of terabytes is very difficult inside memory. So you really need to move to the storage system and do computation inside the storage. Okay, there are many more examples in our paper that's on archive. We need to update this, actually. I actually worked on this. I did a lot of changes, but we didn't push it on archive yet. There's a new version that's going to come up on archive, hopefully by the end of the year. But you can see a lot more examples. Now, let me switch to the other type of processing in memory, which is processing using memory. As I said, this is much harder because we're going to fundamentally exploit the analog operational capabilities of the memory device as opposed to adding logic. Adding logic is easier, in my opinion. But in the end, I think we need to do both because we really want to be efficient. So this is going to be much more efficient fundamentally, but it may not be capable of doing everything in memory as easily, let's say. Okay. So I'm going to focus on, especially on processing using DRAM, although we do have work that shows that very similar things can be done on flash memory also. In existing flash chips, we've shown that you can do a lot of these. We also have a separate research that's going on. Other technologies are also very interesting. Clearly, people have been working on like processing using RRAM, phase change memory, etc. That's also very interesting. But basically, if you let's focus on DRAM. I think there's this joke in memory in general where people say the future of DRAM is always DRAM. I don't think that's true. At some point, I think we'll move to some other technology, and that technology will eat away DRAM, but we're not there yet. I think DRAM still has at least 5 to 10 years to really house our applications. So basically, we can natively support block bitwise operations. I'm going to show you examples. I'm actually going to start with block bitwise copying and initialization, which is also important. DRAM can do random number generation, physical unclonable functions, and more complex computation using lookup tables, mostly at low cost. And we're going to use analog computation capability of DRAM, but this is not purely analog. Purely analog, I think, is difficult. It's important to examine, but it's difficult. But inside DRAM, you already have analog to digital and digital to analog converters. And we're going to take advantage of those digital to analog and analog to digital converters in DRAM. Sense amplifiers, for example, are great analog to digital converters. So we're not going to lose data integrity, at least as much, depending on what you do. So a basic idea will be activating multiple rows. Concurrently or sequentially activating multiple rows performs computation. Now that's interesting. We're going to look at circuit theory, and theoretically, this is possible, as we have shown. Now, what's really fascinating is even commodity off-the-shelf DRAM chips are able to do this. You take a DRAM chip that's not designed for this purpose today, you violate the timing parameters, and we see these functions. So I'm going to talk about that at the end. So you get significant performance energy improvements overall, even larger actually, depending on what you do in the system and your bottleneck. So we're going to start simple with data copy and initialization. This actually, it's always good to start simple. What is the minimum thing that I can do with a new idea or a new technology? And if you look at data copy and initialization, it's everywhere in our applications. In fact, Google, in the paper that I mentioned in 2015, according to them, only these two function calls, memmove and memcopy, occupy 5% of their data center cycles. This is fascinating. Only two function calls is responsible for 5%. Okay, so how do we do data copy today? If you want to copy a source page, let's say 4 kilobytes, to a destination page, you go through the processor. Basically, we use the processor. We tie up the processor unnecessarily. Again, blank slate approach. Give this picture to a, I don't know, 10-year-old kid. Ask the question, to copy these two things that are close to each other in a memory chip, I'm going through the processor. Honestly, they will tell you you're doing the wrong thing. Basically, that's what we should be doing going into the future, in my opinion. It's much easier to do this thing if you have the mechanisms to do that, right? Basically, do the copy inside the memory. This is low latency, low bandwidth on the memory bus, which is a very important resource. No cache pollution, and no unwanted data movement on the memory bus. I'm going to show you a mechanism that takes a 4 kilobyte page copy from about 1 microseconds to 90 nanoseconds, and from 3.6 microjoules to 0.04 microjoules. And the mechanism is going to be very simple. We're going to exploit the internal operational structure of DRAM. So I've shown you the subarray before. We're going to make it a little bit more complicated. We're not going to make it complicated, but I'm going to show you a little bit more in the subarray. Essentially, this is a subarray, which is the basic design unit of DRAM or any type of memory, actually. And we're going to copy one page to another page inside the subarray. Now, the way you can do it today, you can actually do this mostly today. You first activate the first row, which brings the data into the row buffer. Row buffers are sense amplifiers. Essentially, now they amplify the data. The data is strong in the row buffer. The next step we add is to activate the destination row, which concurrently deactivates the source row and connects the sense amplifiers to the row buffer. Now, once you do that, you move the data from the row buffer to the destination row. Essentially, the source row was captured in the row buffer and then put into the destination row. By doing 2 consecutive activates, we moved an entire row. There's negligible hardware cost, and you get significant performance and energy improvements, as we have shown. And our paper showed that in real applications, you get significant performance gains. So this is really extremely small hardware cost. And I'm going to show you that in today's DRAM chips, you can do this almost perfectly with 99.98% reliability, even though DRAM chips are not designed for this purpose. And as I showed you, we didn't add any circuitry, but to make it perfectly reliable, you will need to add some circuitry that I'm not going to talk about right now. Okay, that was data copy. Initialization is another part of data copy. Let's talk about computation. I'm showing you 3 rows over here, A, B, C, 1 bit line, and a sense amplifier. Imagine this row being 8 kilobytes or 4 kilobytes, and imagine many of these subarrays being in present DRAM. So you will be able to do this operation on tens of millions of bits in a single DRAM chip. The operation is triple row activation. The idea is to concurrently activate rows A, B, C. Now, if you do that, these capacitors in DRAM, through their access transistors, get connected to the bit line concurrently. And based on operational circuit principles, charge sharing happens on the bit line. And assuming an idealized circuit with some amount of variation, let's say, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. Now, at the logic level, that's a bitwise majority function. Essentially, the final state is a bitwise majority of A, B, and C. This is bitwise. I'm showing you only one bit in each row, but imagine many bits. Now that's bulk bitwise operation, essentially. Majority function is very interesting. Now I can compute the majority of 3 rows. Now, if you take C out and set it to 1, you get the OR function or the AND function if C is 0. Now you can do bitwise OR and bitwise AND. You're saying, maybe you're thinking, I'm missing a NOT. Yes, you're missing a NOT to be functionally complete or Boolean complete, but it's already there, actually. It's at the bottom. So if you actually activate one row, you get the complement of that row over here. So inversion is already there. You just need to feed it back somehow to this array. I'm not going to talk about it, but that's what we do in the paper. Now, if you have a NOT function, this is functionally complete. You have bulk bitwise majority and NOT, which is functionally complete, or AND and NOT, which is functionally complete. You should be able to express any algorithm to take advantage of the substrate. And I'm going to show you some results that shows that it is actually possible to do that. But before that, there are some algorithms that are naturally a good fit for this sort of substrate. A lot of databases, for example, do bulk bitwise operations using bitmap indices. Some databases are specifically designed for actually this purpose. And some web search engines are also specifically designed for this purpose. We took one database that's designed to maximize bulk bitwise operations, the bitweaving database, and simulated it using our simulators that implement these bulk bitwise functionality. And we see significant end-to-end performance improvements and energy improvements. I will not go into this in detail. There are a lot more results in our paper. And this is 2017. So, by the way, this paper was rejected 4 times before it got published. One of the comments that we have seen was for a reason for rejection, which is a very bad reason, I think. We cannot rebut this comment. The reviewer said, DRAM manufacturers will never implement something like this. Now, as a researcher, I cannot rebut this. This is not objectively rebuttable, right? How can I predict the future and say this idea is not going to be or is going to be implemented by DRAM manufacturers? So if you're getting rejections and if you have a good idea, stay strong. Okay. So as I said, you could make this completely general purpose. This is actually a general purpose substrate. And later, we wanted to make it more programmable. In this work, we essentially design a framework where the user can specify any operation. User can, if you're a hardware designer, you should be able to design any operation using a circuit that looks like this, a convolution, a matrix multiplication, a division, for example, or some sort of linear approximation, or some sort of polynomial evaluation. Anything of any complexity can be designed like a circuit that looks like this. Now we take this circuit, we convert it to a majority inverter graph. We use some design optimization tools that are actually developed for quantum computing, because it turns out quantum computing uses a lot of majority functions also. And we optimize this program, and we generate a sequence of DRAM commands as a microprogram. Now you can associate this operation, we call it bulk bitwise operation, with a microprogram. Again, it could be any operation, convolution, for example. We show in our paper with convolutions. And then when the program uses this operation, this function, this instruction gets shipped to the memory controller, and memory controller fetches the microprogram and executes the microprogram. This microprogram does triple row activation, row copy, row clone, etc. Everything that we talked about earlier. It is composed of these primitives that can do data copy, data initialization, and computation in DRAM in different ways. And the result gets returned inside the memory. Okay, so I will not go into a lot of detail. This is a full system framework, but showing, we simulated this, and we show that you can actually improve performance and energy efficiency compared to what we've shown earlier on many complex DRAM operations as well. More recent, this is the paper that talks about it. More recently, at the beginning of this year, we published an improvement over this work. This is called MIM-DRAM. And in this work, we basically make this more flexible and more programmable. Essentially, here the idea is, as opposed to doing computation on a very large row, you can actually do computation on a small fraction of it. Now, if you are able to do computation on a very small fraction, this way you can actually improve efficiency, and you can do other operations on the rest of the row. I will very quickly go over this because we don't have that much time. The idea is to have a fine-grained access to DRAM. Now, we're going into a little bit more detail into DRAM architecture. If you look at a row consists of, this is a subarray. It consists of multiple mats. I'm showing you 4 mats over here, but it actually is 16 mats, maybe 32 mats, etc. Now, instead of doing operations, a triple row activation on the entire row, we are able to do this on a small fraction of it. This is called fine-grained access. We segment the global word line to access individual DRAM mats. And there are a lot of works that actually proposed this in the past. We have a new version that's actually lower overhead, in our opinion, and in our evaluation. If you're interested, you can actually look at that paper in TACO that's going to be presented soon. But once you do that, you can improve utilization of these subarrays because you don't need to activate this part of the subarray. And on the other side, you can do other things. For example, an operation happens from one application over here, another operation happens from another application over here. It doesn't have to be other applications. It could be the same application as we showed in this work. We also do some, add some more interconnect inside DM so that we can do reduction operations, which is really important. This is processing near memory now. We're adding additional logic to the reduction operation. I think that's important, as I said. Going into the future, we need to add more interconnects, more computation. And we have a compiler to generate vector instructions that could be executed on the smaller set of columns. This is actually important. This is one of the main reasons why we try to reduce the granularity of the operation. Because today's compilers are not good at discovering parallelism that are 8 kilobytes or 4 kilobytes. But they are designed to discover parallelism that are 8 kilobits or 4 kilobits. But anyway, bytes, you just multiply. They're designed to discover parallelism that is within the scope of the processor's SIMD width. So for example, 128 bits, 512 bits. So we target the LLVM compiler so that we can extract SIMD parallelism from an application and schedule these processing using DRAM instructions. Again, I will not go into the details. This is going to be online. Well, the paper is online, but our source code will be completely online very soon. And the results that we see are significant. This is an updated set of results with a better compilation strategy, etc. And we on workloads where we can do this efficiently, we get significant performance energy efficiency improvements compared to CPUs and GPUs. So GPUs are actually very good at exploiting this bit level parallelism, but they're extremely inefficient. If you look at performance, GPU performance is higher. But if you look at energy, GPU energy is horrible. So that's why we see significant energy improvements compared to GPUs. Okay. Any questions? Yes, over there. Do we need to? I may not be able to hear. Sorry.
Hey, when we are optimizing the when we are optimizing the CPU pictures, that we are told to optimize the most frequent cases.
Yeah.
So as we are uploading the computation to DRAM using the memory, so what do you think are the most frequent cases in DRAM computation?
Yeah. Yeah, so that's a very general question. So there are two answers to that. If you want to, so we have actually some works that I didn't talk about that are in the later part of the slides, where you identify what are the bottlenecks that can be accelerated on the memory side. We have a work that's called DAMU, which really classifies an application's processing into 6 types of bottlenecks. And some of those bottlenecks are functions that require that have very low arithmetic intensity and that don't have very good locality. So if you can somehow identify the bottlenecks in your program using tools like this, those tools can help you offload what kind of functions. So in that sense, we need to develop the infrastructure to identify those things. I cannot tell you, for example, this function will be bottleneck, this function will be bottleneck. You really need to do some analysis on the function. That's true for CPU also, by the way. I'm not going to that detail. But there's another answer to this, which is like similar to what I just described. We're not there yet, in the sense that if you actually design a paradigm that is fundamentally capable of this sort of computation, we really need to rethink how we write applications and how we write compilers to first perform computation, and then we start doing optimization. That's what happened in the CPU domain also, except it happened many, many years ago, like 60, 40, 50 years ago. People actually first were able to do computation, and then they started optimizing the bottlenecks on the CPU. I think memory-centric computing is similar. We first do computation over there, and then we start optimizing the bottlenecks. Hopefully that gives you an idea. Okay, one more question. Yes. Yeah. 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 Yeah, that's a very good question. That's something that needs to be looked at, essentially. And there are some works that try to do both. Clearly, the reason we do interleaving the way we do today is where we do computation only in the processor, right? But once we start doing computation on the memory side, the interleaving needs to change. So there needs to be some data mapping mechanisms. But these are some part of the adoption issues that need to be solved in research and development. No question about that. Okay, one more question here. Go ahead. Okay, that's great. Mm-hmm. That's right.
How do you think that in your work and within the can kind of contribute how much to the overall optimization?
Yeah. Yeah, I mean, that's a long question. First of all, I think it's very important. Compilers, the whole stack is important, but we need to revisit the compilers also from a data-centric, memory-centric paradigm. And we need to think about how we design compilers for processing using memory, processing near memory. No question about that. How much did the compiler contribute? That's a very interesting question. It did have contribution. You should ask that question to my student Geraldo. But the contribution is really, it's very hard to isolate just the compiler contribution, I should say, because we do multiple things to enable the compiler to work on it. And if you don't do those hardware changes to enable the compiler to target smaller mats, for example, then the compiler itself is not going to buy you much. So it's really, compiler contributes some, but together with the hardware, you get a whole lot more. Does that make sense? So you really need to design the hardware and the compiler together. Okay, one more question. Okay.
For in memory or in storage computing, we know such technologies we need to develop new hardware and modify the software.
Yeah.
So it's hard to deploy such technologies in real world systems. On the other hand, to minimize data transfer, we can improve the cache size. For example, through 3D stacking and improve the memory capacity. For example, we can use CXL. And also, we can improve the performance by use faster data bus. There are many interconnection technologies. For example, PCIe is faster and faster after each generation. So if we have larger cache and memory and faster data bus, so can we solve the data transfer problem through this simple way, but instead of develop the in-memory or in storage computing?
My answer is no. Because essentially, yes, you can add a lot, but there will be some applications that will benefit, but there are a lot of other applications that won't benefit. Like that's what we have shown with the machine learning accelerator with Google, right? You could keep designing an accelerator that's bigger and bigger and bigger and bigger. But you're really, first of all, racing against something that's becoming increasingly data intensive. And also, I wouldn't say that's a simple solution. That's a solution that's easy. Easy is, well, I guess you can define simplicity in terms of ease, but it's easy because we know how to do it. But there's a lot of cost associated with that solution, right? Which is a lot of hardware that you keep adding and a lot of technology that you keep improving. If you actually go to another solution, which is in-memory processing, you could actually reduce the complexity a lot more. So yes, the answer is no, probably. Yeah.
System research, and it's good to improve the system performance by, for example, 20%. It's very good. But for architecture papers, we often see the improvement are tens or even hundreds times improvement. So how, and architecture research, you only use simulation. So how credible are the results?
Well, I think I would not focus too much on the numbers as much at this point. Like, It also depends, like what type of architecture. Like this, a lot of the things that we have discussed here are changing the entire system, right? You're changing both the hardware, software, compiler. And if you actually do that, you gain a lot of benefits. And you customize, and then you gain a lot of benefits. It's very different from a system where you change some components, but you're very limited in what you change. So there's a difference in this type of research, right? They're both valuable, but in one type of research, for example, I do a lot of research on processor microarchitecture also. The results that we get over there are 5%, 10%, maybe 15% if you're lucky. But we're very limited in what we can change, because there are a lot of other constraints that you need to deal with in the system, and you cannot change them. You just change one component, and that's what gives you 10, 15%, even if you try to optimize other things around. So here you have a lot of freedom. And once you have a lot of freedom, then you can explore the design space much better. That's what enables you to get to, in my opinion, larger numbers. There's always errors in simulation, no question about that. But that's always been true. In the 1940s, 50s, 60s, 70s, 80s, 90s, 20s, when people have ideas, new ideas that were different, they could not build a system to evaluate it. But they actually argued for the ideas in intuitive ways, or using simulation methods, using analytical modeling. And eventually these ideas were built and they became real. Right? So I would not focus too much on the numbers. There are different types of research for sure. And these will lead to different sort of numbers, but it's good to focus on the ideas and what they could enable at a higher level. Okay. So now let me give you, that said, let me give you something that shows that, okay, we had the same concern in a sense. We basically said, okay, these ideas are very interesting. We could prove them in simulation, both circuit simulation and also system simulation. Very interesting results. Can we do some of this in real hardware? Now, if you think about DRAM, real hardware is very difficult because it's very hard to manufacture DRAM, and it's very hard to manufacture DRAM at the nodes that we can manufacture DRAM in the global world today. So what we did was actually to understand whether existing DRAM chips can perform some of these things. And if they can, then this gives us an indication that we're really on the right path. And I'm going to show you results that show that. Essentially, existing DRAM chips can perform almost all the operations that we envisioned using simulation. So this is a framework that we built. It's called PyDRAM, FPGA-based framework. We showed that you can do row clone and true random number generation using off-the-shelf DRAM chip. The idea is to violate the timing parameters. If you violate the timing parameter between two consecutive activates that go to the same subarray, you actually get the row clone function. If you violate the timing parameter to access data, you get some cells that are failing randomly. That's a true random number generator. And we built this end-to-end framework, which looks like this. It's essentially an FPGA. In this FPGA, you have a RISC-V processor, very simple one. And we change the operating system and the compilation flow, etc., such that whenever you have a page copy, that page copy is allocated to the same subarray. Well, not all page copies, but whenever you can do it. And that page copy operation gets shipped to the memory controller inside the RISC-V processor. And the memory controller violates the timing parameters between two activations to the subarray and copies the source page to the destination page inside the memory. So you can do it in an existing system today. You can actually download the source code, etc. You can use it. We'd be happy to support it. It's a lot of system engineering. And in the end, we're happy to support also. You see these results in the paper that show that you can actually do the data initialization and copy inside the DRAM, and you get significant performance improvements. The reason the performance improvements are extremely high over here is because the RISC-V processor that's over there is very simple and wimpy. It's only 50 megahertz, for example. So as a result, it doesn't have a lot of tolerance. Okay, so if people are interested, this is an example where we show in real DRAM chips you can do this. But you can do more. This is a paper that we published, again, in HPCA this year. I'm going to cover this in a little bit more detail. Well, actually, in two papers, and in this HPCA paper and then a later DSN paper, we showed that three major results. One is you can copy one row into up to 31 other rows with almost perfect success rate, as you can see. You can perform the NOT operation with up to 32 output operands in real DRAM chips. You can also perform AND, NAND, OR, and NOR operations with 16 input, up to 16 input operands, with a reasonably high reliability, more than 94%. I think these results are fascinating. I truly believe this is fascinating because First, DRAM chips are not designed for this purpose, right? If you go to a DRAM manufacturer, in fact, we talked with a lot of DRAM manufacturers and described our results. They say they're fascinated in the sense that they didn't know their chips are capable of doing this, because clearly no DRAM manufacturer is going to advertise this to you. In fact, they're now examining how they can actually do this more and more reliable based on our results. The second thing is, these are quite reliable. That number over there, almost perfect reliability without changing anything in the DRAM chip, anything in the DRAM interface, just violating the timing parameter, the memory controller, is fascinating. These are also quite reliable. These are actually analog operations, and we activate a lot of rows concurrently. You would think these may not be reliable, but we get more than 90% reliability in many of these operations. Of course, the goal is to make these 100% reliable, if possible, and that requires changes to the DRAM chips, and we should be doing that. Now, let me give you an example. So basically, what we do with multi-row copies, we simultaneously activate many rows. We activate the source row, and then after that, we activate many rows in the same subarray by violating the timing parameters in a specific way that's described in the paper. This way, we can copy one row to many destination rows, which is very interesting. Not operation. I've already said this, so I'll go through this quickly. Basically, if you have a source subarray that's over here and the destination subarray that's over here, they're connected through a sense amplifier over here. We first activate the source row, which essentially starts the charge sense amplification process. And the complement of the data is actually here. And then we violate the timing parameter, which activates the destination row. And the data that's complement of A gets latched on the destination row. And we show this in real DRAM chips. Now, the more difficult part is more complex functions like NAND, NOR, AND, and OR. Essentially, here you can manipulate the bitline voltage. So assume that you have two subarrays. I'm showing you only 2 rows over here and 2 rows over here. You concurrently activate all of them by violating timing parameters in the memory controller. There's a specific way of doing this. What you get at the circuit level is you get the average voltage, A and B over here, and average voltage of X and Y over here. And the sense amplifier compares the function, computes the function of whether the average voltage over here is greater than the average voltage over here. Now, if you know this, you can manipulate the voltage specifically to compute things. Let me give you one example. If in the reference subarray, the average voltage is set to be 3 VDD over 4, and there is a way to do that, what you compute in the compute subarray is an AND function of X and Y. And the result, the NAND is over here also. So basically, you can do AND and NAND functions. Similarly, you can do OR and NOR functions by setting the reference subarray average voltage to 0.5 VDD. There's a specific way of doing this in real DRAM chips. You can actually do this reasonably reliably, as I will show you. This is fascinating, I think. Okay. So in the paper, we show how to do this carefully. We actually release all of our source code. People can replicate this. You can please let us know if you're interested in doing more of this. So we tested this on real DRAM chips using our DRAM vendor infrastructure that enabled us to figure out a lot about the DRAM chips on major manufacturers. This is just some example. Row copy, as you can see, the success rate of row copy is almost 100%. It depends on the number of destination rows, but not that much, as you can see. Right? Your destination row can be only 1 or 31. So you can do row copy across a good chunk of the subarray. This is NAND, AND, OR, and NOR. And you can see that the success rate of these operations can also be quite high, 94%. We're still understanding where are the errors, where are they happening, so that we can actually fix these errors also, or provide mechanisms in a sense amplifier or row decoder circuitry so that we can make things more robust. But the fact that the numbers are quite high is quite promising. This shows that as we kind of envision or hypothesize based on circuit level operational principles, these DRAM chips in real life are actually quite capable of doing things. Okay. So these are the 2 papers that we published this year. One is at HPCA, the other is at DSN. And all of the code is all open. People can test it themselves. All of our code is open for our DRAM testing infrastructure also. Then the question becomes, what else can we do using commodity memories? I will not go into this in detail, but in the past, we have shown that you can do true random number generation in DRAM. Again, real DRAM chips using results from 3 major manufacturers, sometimes 4 major manufacturers. By reducing the timing parameters to access memory, you can find that some DRAM cells fail randomly. And those DRAM cells can be random number generators that are high throughput, low energy. We have better ways of doing this. In fact, at IEDM, we have a paper coming up that talks about better ways of doing this that I'm not going to talk about right now. You need to design the system around it. And some cells fail quite reliably when you violate the timing parameter, then they form a signature of the device. So you can actually have a physical unclonable function. If you want more complex functions, you can do lookup tables. Again, I will not go into the detail. And as I said, you can do almost all of these functions in flash memory, SSDs. We show with real flash memory chips that you can do these also. And we have some work coming up that actually shows that you can do even more in flash memory. Now that I've covered two types and giving you some examples, let's talk about some adoption issues. Before that, I should tell you that there's a lot more that we cover in this paper and the new version of it that's coming up this year. Adoption is always important, meaning you can design any hardware I believe, actually, truly believe that any hardware can be designed. It may not be reliable, but more than reliability, it may not be usable. And adoption is all about making the hardware usable, right? And if we want to adopt a new paradigm, we really need to solve a lot of adoption issues. And if you look at these adoption issues, then clearly there's infrastructure and hardware at some point, but it's mostly about software and system and making this doable. Application and software, programming, system and security support, data mapping support, for example, we have discussed earlier briefly. How do you design the runtime and compilation systems? I think all of them are important to solve. There's work going on in this area. And in my opinion, the hardest part is really the mindset, meaning going back to what I just described earlier at the beginning of the talk, the way we design our computers today is completely processor-centric. Our mindset is processor-centric. When you look at every single decision that you make in the design of a computer, it assumes implicitly, mostly implicitly, sometimes explicitly, that the data needs to move to a central unit where it can be processed. Whether that central unit is a processor, GPU, CPU, accelerator, it's still a central unit. It's very compute-centric. We need to re-examine all of these choices. And clearly that requires a will and a mindset change. Okay, so I think we need to really examine the entire stack to get to a memory-centric mindset. That said, I think we have a lot of works on programmability that I'm not going to talk about right now. Compilation is important. These are some works that I will flash to you. In fact, we have designed high-level frameworks to essentially do programming in general-purpose processing in memory chips. This is a tool that we mentioned earlier to decide which bottlenecks exist and which bottlenecks should be offloaded to near memory processors. And we have some other things that I'm not going to talk about. Coherence is an important problem to solve because when your data is partitioned across different accelerators, you always have a coherence problem. And we have some works on that, but there needs to be more work in that area, I think. Synchronization is important. We have some works. I think one of the toughest problems is virtual memory, how to actually handle address translations. These slides I will send to my host, so if you're interested in the references, you will have all these slides, hopefully. I think virtual memory is one of the toughest things. We really need to re-examine how we design virtual memory. This is another example that has not changed for a long time. Like virtual memory has been around for 50, 60, 70, 80 years. And unfortunately, it has not changed much, and we need to re-examine it. So we built a lot of evaluation infrastructures, some of which I have talked about. I think that's really important to build going into the future so that we can evaluate these mechanisms. Okay, so I'm giving you some examples over here. Let me conclude. And then I'll take more questions if people are interested. So I think going forward, we want fundamentally energy efficient architectures that requires us to be much more data centric. We also want fundamentally high performance architectures, and that also requires us to be data centric. In fact, I think if you change this high performance to robust, secure, sustainable, I think all of them require us to be data centric. And this requires us to rethink our architecture so that we can minimize data movement. So to conclude, I think to get there, we really need to enable computation capability inside and close to memory and all of the places where data is input or output. This can hopefully lead to orders of magnitude improvements. I've shown you examples of that today. I believe this can also lead to enabling new applications and computing platforms. For example, some genomics platforms that we don't have today that could be mobile, etc. It can enable a better understanding of nature because I don't think nature is processor-centric. It's much more data-centric and also data-driven and data-aware, which I didn't define, but I'd be happy to talk about. And who knows what else. So I think the future of memory-centric computing is really bright. And the good news is, 10 years after I'm in Wuhan right now, I have a lot of improvements to show over here, as you have seen. But we do still need to do research and design across the computing stack. So I will show this picture of this machine. This is, I believe, a sort of machine. We don't understand this machine very well. And I think there's research going on here in mapping this machine, understanding this machine within the boundaries of these buildings, right? Which is great. But I think what we do know about this machine is it's very heterogeneous, and its data and computation is meshed in a way that we don't do in our computers today. Today's computers resemble nothing like this, in my opinion. And it's good to think about that. Okay, I already said this. I think I will say that we put a lot of work open source. I strongly believe in open sourcing essentially everything as much as possible. And you can find our papers as well as open source tools. Essentially everything that I discussed today is open source. You can find it online somewhere. And if you cannot find something, please let us know. I'll acknowledge the funding that we receive. And most importantly, I'll acknowledge my students. They are the ones who have done all of this work. And you can find some pictures of them here and some newsletters where we actually talk about what they do in their research. And we have PIM tutorials. If you're interested in doing work on processing in memory, memory-centric computing, we organize a lot of tutorials starting with 2023. The last one was held at Micro this year. And there's one coming up next year at PPOP, Principles of Programming Language. No, but ACM PPOP. If somebody can fill that. Principles on Practice of Parallel Programming. Okay, that's good. Yeah, we wanted to organize a workshop or tutorial on PIM on a parallel programming conference, because I think it's really important to think about enabling that. And we have a workshop coming up at ASPLOS next year. And this is all open source. You can find this on YouTube and online. Everything is online. With that, I'll conclude. I'm happy to take more questions.
I think generally, students may like to ask questions.
Okay, sure.
I think that we have.
Okay, there are more questions. That's great.
Yeah.
I see you verify you verify using like in the real world. I think you should use put it in a small script, and I personally plug the DRAM myself in server. I think the space is very limited.
Mm-hmm.
It's full of small flag chips. So the question for me is, I think the space is very limited. You have very limited design space in it. If you add more computing logic in it, you may have to trade off capacity for computability. And I'm not quite sure if you plug many DRAM with computability into the system, does it use more keys?
Yeah. I mean, certainly, yes. So I think the answer is yes, it will affect your storage capacity. No question about that. Whenever you add some logic to a chip that performs computation, like near memory computation, you will need some space. And for example, the UpMem company, what they did was they actually added a full processor, a full MIMD processor next to each DRAM bank. And the overhead that they have is significant. But the benefits you get in some applications is also significant. So the question is, what are you willing to add, right? I believe what they did is a bit expensive, no question about that. We have a lot of analysis of their chips, which is actually very interesting. And if people are working on the system level, UpMem is something you can buy, for example, to actually or work with them or work with us so that you can get access to the chips and you can evaluate things. We need to find ways of designing memory chips. The reason today we're in this mindset where memory chip is memory. We designed for memory, and capacity is the only optimization point. If that's the only optimization point, and if you want that to be the only optimization point, you can never get somewhere else. Then we're doomed. Meaning we should always design memory as capacity. I think we should take a step back. And I hope this is helping. This discussion is helping that. If we take a step back, today capacity is everything, and then there's a computation processors where capacity is almost nothing, whereas computation is everything. Right? We need to find a balance where we design a memory chip that has some computation capability without a whole lot of cost, right? And we need to explore that space right now. And I believe there are ways of doing that. For example, the processing using memory approach is one way, but having small functions to add to the DRAM chip. Now, with two-dimensional technologies, if you have a planar memory, clearly there's not a lot of room to play with. But once you go to three-dimensional technologies, you can add logic underneath memory layers, and your cost is kind of hidden, right? Now you're not really reducing capacity. Yes, you can always say one layer can be more memory. You're always losing capacity from that perspective. But I believe we need to, you cannot get something without paying for some cost. Does that make sense? The question is how much cost you can tolerate and what kind of system level benefits you get. Okay. The other question that you had was heat. And that's again always a question, basically, meaning power. And again, my answer over here is yes, you need to do that. So today, for example, the reason we think about memory as memory is memory does nothing else other than serving data. And that's why it doesn't have a lot of heat. You don't need to have put a lot of power into it. But if you go to a paradigm where memory can also do compute, you need to supply the power. You need to actually take out the heat. So essentially, we need to think about memory as a computation unit. Hopefully that makes sense. Memory needs to do what? Mm-hmm. I mean, certainly, for example, my cell phone is consuming power doing refresh right now, right? Self-refresh. That's true, assuming it's DRAM. And it's DRAM. Refresh does consume power, but if you add computation capability, you will have a lot more power on the memory. Even with processing using memory, if you actually use all those memory cells to do computation, that will increase the power consumption. And you will need to increase the power requirements. Sure. Okay, multiple questions.
I'm also papers and I found out that many of them use the small or medium size application. For example, 3-layer MLP, 5 layers in Excel. What if we use, for example, GPT, if possible?
Yeah.
I think one chip or one different rank will not be able to store all this data. So we need many chips and ranks and interconnects between them.
Yeah.
And we also know that the intermediate data is also huge in our side neural networks. So the data transfer is also a new problem.
Yeah.
And in this situation, will the tremendous merits of processing unit memory, for example, high performance, low energy cost, still stand?
Yeah. I hope so, but I don't know the answer. The research needs to be done, right? And I think that's a great research topic. My perspective is that we need to examine every single important application and look at how it can be implemented nicely in processing using memory. That's part of the adoption issues. And I think that's a great research topic. Like, can I make GPT or LLM, large language models, work inference? Not even training maybe, but even training how do I actually make it work on a processing using memory system? And I agree with you. You really need to have multiple ranks and multiple chips, and you need to handle the data movement within those, etc. But that is something that's actually a great research problem. If you think about it, there's a lot of resources dedicated to looking at and optimizing these important applications from a processor-centric point of view, right? A lot of people are looking at it. It's good to have some smart people looking at the other side. How do I do this in a memory-centric way? And I think that's actually great, because if everybody is looking over here and nobody's looking over here, then everybody's thinking the same way.
Thank you very much, Professor Mutlu. The same thing for body information system about the scalability, right? Whether it be computing memory or for PRM, which we share some of your opinion about the scalability thing.
Yeah, I mean, scalability is important, certainly, right? You need to scale. I think one of the previous question also tackles scalability a little bit. If you have very large applications, how do you scale? And I think there's nothing that fundamentally limits the scalability of processing in memory, right? Because in the ideal form, what you do is really you attach a processing element to every cell. Like that's what processing using memory is, right? And that processing element is as scalable as your memory. As the number of cells increases, your computation capability increases. In fact, in our earlier work, Tesseract, that I mentioned, our argument was that you want performance that's scalable with memory capacity. In today's systems, like processor-centric system, your performance doesn't scale with memory capacity because you have a bandwidth bottleneck, you have a data movement bottleneck. If you actually have computation capability on the memory side, your scalability can be even better than today. Does that make sense? Of course, this needs to come with power costs, as was mentioned earlier, and heating that you need to deal with. But fundamentally, I think scalability is of processing near memory is maybe even better than existing systems. Okay.
Thanks for the report. Let me see from the system view. Current system put a lot of efforts on the virtualization and scheduling. My question is, besides put the computing in the memory, if we also require to put like virtualization and scheduling into the memory?
Yeah. So I think that's a great question. Those are part of the adoption issues that I didn't get a chance to discuss much. But virtualization is going to be important to handle, right? That's part of virtual memory, but general virtualization system and scheduling, right? I believe we need to revisit how to virtualize these systems. We're not there yet again. And we need to do more research in that area. But we also need to do scheduling to decide what to execute where. And part of that functionality could be in the memory side as well. Sorry, I don't have a better answer, but there needs to be more research in that area for sure. Yes. Hopefully these questions also show you that how little research has been done in these areas on memory-centric computing, because it's a relatively new paradigm still, right? Even though the original ideas were from 1960s, people really didn't examine a lot of these things because of this mindset issue, in my opinion, right? But once we change the mindset, there's a lot of resources that you dedicate over here, and hopefully we can have a much more efficient computing paradigm 10 years down the road.
Okay.
Okay, there's one more. Okay, yeah, sure.
So we have the last one.
Okay, last one. Okay. Yeah. Okay.
Great. Fantastic talk. So I have a question. So is it possible optimizing to use new DRAM cell structures to for processing using memory?
Yeah.
So as far as I know, so in the device community, for example, in the IEDM conference, some people propose to use two transistor zero capacitor, so the embedded DRAM to do the math computation. So do you think can be accepted by the industrial point of view?
Yeah.
Thank you.
Yeah, that's a great question. And I think that there needs to be more research in that area also. So how do I fundamentally change or optimize the DRAM cell structure such that I can fundamentally do better computation, right? More efficient computation. And I agree that there have been some proposals. It remains to be seen whether they'll be accepted by industry. Industry is always slow moving, right? It's very difficult. I think one of the issues with embedded DRAM is we don't have the infrastructure as much, right? People have built a lot of infrastructure to optimize the 1T, 1C type of DRAM. Now going and asking that industry to do 2T is saying, get rid of all of your infrastructure almost and retarget it completely. So I think we should not be concerned as much about maybe the old industry, but we should think about creating new industries that can enable some of these new technologies. That's one way of actually making these ideas real, maybe faster, right? Because old industry will always try to amortize the costs and the investment they've made for many decades. So their initial inclination for any new idea will be, I don't want to do it. But this doesn't mean that the new ideas are bad. This just means that new ideas will take time to get adopted and need different mechanisms to get adopted than pushing the old industry to do something new, right? It's kind of like in English, there's this term, teaching an old dog to do new tricks. Sometimes it's tough to do that, right? If the dog is younger, you can teach them to do new tricks much more easily. So I see some of these industries as old dogs. Sorry, no pun intended over there. It's very difficult to teach them new tricks because they don't want to do new tricks. Does that make sense? Yeah, sure. Okay, one more question, sure. A real last one. Okay.
This is a very interesting talk, and your group is doing a very good research. So my question is, if I just wonder if you can give our students some advice on how to do an excellent research and public papers on top journals and conferences, or ideally won the best paper award.
Yeah.
Okay.
Okay, that's a great question. That's a longer answer maybe, but yeah, briefly, I think certainly choosing a problem that is really important and where you can make a big contribution that's different from what everybody else is doing could be very useful. That's a good starting point, choosing an important problem where you can make a big contribution. I think that's a good starting point. Of course, this should be something you're very excited about, meaning you should be dedicating like kind of yourself. Like in my opinion, research is a lifestyle, right? I don't do research. I don't see it as work. It's more of a lifestyle, right? I look at everything as research. And when I try to come up with ideas, do something, I dedicate myself to it, right? And I think doing great research requires that sort of dedication. And of course, writing papers require a lot of focus on not just coming up with an important problem and then coming up with good ideas, coming up with good results, doing all of the things that you need to do good science like simulation, implementation, evaluation. On top of that, you need to write well, communicate well. So there needs to be a way of actually structuring the story so that somebody else who doesn't think about this or hasn't ever thought about it will understand it and will say, aha, I understand the problem these people are telling me, and I really think this is very interesting and this is a good idea. If you get someone to be excited that way, I think by doing the storytelling and writing in a nice way, in addition to everything else being done right, of course, then I think there's a better chance for getting the ideas adopted and also having more widespread impact. That's just a summary. Of course, there's a lot that goes into all of that, I think.
Thank you very much.
Sure. Thank you. Thank you for a lot of questions. Yes. Okay.